Hello everyone, we are Team Vicor Corporation, and today we will be presenting our project, the Standalone Cable Checker, also known as SCC for short. So over at Vicor Corporation, the technical directors that we have been under the guidance of this year are Daniel Hartnett, who was from the ELE class of 2021, Alfred Binder, and Nathan Shake, who was from the ELE class of 2020. Our team consists of 3 members, as you can see. On the left side is me, Alan Lee, and my major is electrical engineering. In the middle, we have Ricky Lau, who is our CPE. And on the right side, we have Griffin Melican, who is also an electrical engineer. So who exactly is Vicor Corporation, and what exactly do they do? Vicor Corporation is a company based in Andover, Mass. However, they have many facilities stretching across the United States and also internationally as well. They are a huge manufacturer of modular power components, and they are a vendor for various industries that you might be a part of. Some of them include automation, industrial, high-performance computing, defense, vehicles and transportation, aerospace, and network infrastructure. Vicor Corporation and ELECOMP URI have worked together closely over the past couple of years to create many hardware checkers. These hardware checkers allow for the test engineers at Vicor Corporation to test their ICs much more smoothly and quickly. This is because it offers a plug-and test solution that allows for the testing to run in the background. However, one issue that they currently have is that there are many cables that need to be interfaced with these ICs as well. Unfortunately, they do not have any hardware checkers for this type of situation. This means that the test engineers over at Vicor need to test each pin individually. Since they use a large variety of cables, some ranging up to 170 pins, this means that they have to manually test these. This causes for the debugging process to be tedious and time-consuming as well. Our project aims to solve this. We aim to create a housed, standalone cable checker that will allow for multiple cable connections for a wide variety of cables. The key features of this project will include a cable interfacing that is interoperable with all of the cable types that Vicor Corporation currently uses. It will also feature a UI that displays information regarding these cables. Additionally, we will also have a manual and automatic testing mode. This way, if a test engineer decides to try and repair a cable, they can go back to the pin that was returning an error. Throughout the semester, the Vicor Corporation team has made steady progress towards completing our anticipated best outcome. Some of our team key technical accomplishments include benchmarking components, which consisted of our ICs, which were, in this case, demuxes and muxes, and our microcontroller as well, which is the Arduino Mega 2560. We decided to opt for the Arduino Mega 2560 because it offered a lot more pinouts than our original Arduino, which was the Arduino Uno. Additionally, we have also completed prototype development. Our first prototype consisted of an AND gate that combined the I/O pins from an Arduino, and it would light up an LED if the cable connection was good. If one of the lines were disconnected, the LED would turn off, signaling a bad connection. We realized that this would create a large bubble logic and also a very bulky circuit, which would not be ideal. So we decided to go with a demux and mux iteration instead. This prototype had 3 stages to it. The first stage was really more of us testing on how to use a demux and mux, mostly because we were not familiar with how to use them. The next stage involved implementing manual and automatic incrementation for the address lines. The third step involved really more of adding 3 layers to the mux and demux signal splitting and combining logic. We'll talk about this later, but essentially this made the splitting and combining of the signals much more efficient and allowed us to use a lot less pinouts. We also completed custom footprints for the headers that would be interfaced with the cables that Vicor Corporation has provided us. We needed to create custom headers because there are no footprints available in the Altium libraries or the Circuit Maker libraries. This meant that we had to make them ourselves. Additionally, we have also completed the PCB design for one iteration of the PCB board. We intend to fabricate this and test it out in the following semester. Then, if it works, we will create more versions of it using the other headers, and if there are changes that need to be made, we will do so accordingly as well. So what are the economic implications this project has for Vicor Corporation? One major economic impact is that there will be greatly reduced testing lead times. This is because the project aims to give the test engineers over at Vicor Corporation a plug-and-test solution. This allows for them to test their cables on in the background as they perform more pressing tasks that they have been assigned throughout the day. Additionally, this automatic testing will also mean that there is less chance of human failure, meaning that if a cable is bad, there's a higher chance of the cable checker detecting that as opposed to a human probing the pins manually. Additionally, it will also save them money in the sense that currently, Vicor Corporation might feel inclined to buy new cables to interface with their ICs instead of testing the old ones because it is such a tedious project. Additionally, this will also lead to faster turnaround times because if they know that the cable is not the problem, then the only thing left is the ICs, meaning that they can try to debug the ICs faster. As you can see on the left-hand side is our block diagram which contains the logic for our project. It starts off with the user selecting the pin count for the current cable, which is because the cables at Vicor Corporation are different. This means that some cables will not have the same pin counts. These pin counts will represent the amount of address lines needed. The Arduino sends the signals through the pins depending on the address lines needed, which is then split up by demuxes. These signals then travel through a cable which is wired to the demux on one end, and on the other end it is wired to a mux. These muxes then recombine these signals, and the Arduino verifies that if the signal is good or not. This information is displayed through an LCD. On the right hand side, you can see the 3-tier logic which will be required for cables that have more than 170 pin outs. This is because each mux has 8 different output pins. Some of my key technical accomplishments for this semester include the breadboard prototypes. On the left-hand side, we can see the simple AND gate design, which includes an AND gate chip, an Arduino Uno, and 2 manual incrementation buttons, one for increment and one for decrement. The AND gate chip took in 2 signals from the Arduino Uno, and it will combine them into one and will light up an LED depending on if the signal was good or not. A good signal was represented by both of the lines being active high, or 1 and 1, and a bad signal was represented by if either one of the lines were active low, meaning that they were 0 for either one of them. We tested this by unplugging one of the lines, and if the LED turned off, then the signal was represented as bad. This worked, and we could increment or decrement the address lines to change which LED was being lit up. On the right-hand side, we have the more recent design, which is the multi-level demux and mux design. This design includes signal manipulation through the multiple address lines. Also, it included more incrementation styles, mainly the automatic incrementation style, which ran through all the address lines by itself. It also included an LCD which displayed information regarding the signal lines, which was telling you if the signal was good or bad. And this includes the 2-layer design. We couldn't do a 3-layer design because it required too many pin outs, and the Arduino Uno did not have sufficient pins. Another key technical accomplishment is the PCB footprint and connections. There are 3 schematics here that we can see, the first being the main schematic, which houses all of the varied components that you see on the top level. This includes the Arduino, the first layer of muxes and demuxes, as well as the LCD and the 3 buttons. These 3 buttons allow for increment and decrement of address lines in manual mode, and also a mode change from manual to automatic and automatic to manual. In the middle schematic are the header connections for the mux side, so the output side of the cables. The demux side looks functionally similar, except instead of going to the mux lines, it goes to the demux lines. On the right-hand side, we can see a schematic for the muxes. This schematic contains the second level, which we can see on the left-hand side is the second level demux, and on the right-hand side is 4 out of the 8 demuxes for the third layer. There are 3 schematics of these demux sets, and similarly, there are 3 schematics for the muxes. The muxes look similar to the demux schematics, except instead of outputs, they're all inputs from the cable headers. Some of my key technical accomplishments that I intend to complete before the end of next semester to reach our ABO include finishing the PCB design for the 170-pin cable version of the SVC. This is because we decided to create a separate unit due to the 170-pin cable being too bulky to interface alongside the other cables. I also need to fabricate this board and also test it in order to debug it and make sure that it is ready for Vicor Corporation to use as a plug-and test solution. I also need to create a custom housing unit. A custom housing unit would look something similar to the box on the top left side, where it allows for the user to essentially just plug in their cables and display information on an LCD. Next up, my partner, Griffin Melican, will also be presenting his key technical accomplishments.
Alright, so my focus will be discussing the multiple logic levels of the multiplexers and demultiplexers, as well as the integration of the cables themselves to the platform, which is shown right here. Here we have the symbols and footprints for 2 overheaders, a 20 position and a 34 position. They each have similar parameters for dimensions and pad sizes per the datasheet, and their custom design was fairly straightforward. Here we see the other header's symbol and footprint, this one being a 50 position. Additionally, we also had to design the symbol and footprint for the LCD that we chose. This slide focuses on the mirror logic surrounding our cable headers designed in the last slides. The demux logic spreads out a single input test signal to possibly 50 separate pins, in this case it's capable of 20, 34, and 50. Similarly, the mux logic condenses the 50 separate pins down to an individual output signal, which can be relayed back for analysis. In part with the 3-bit serial address and assigned enable signals, the system allows for multiple different cables to be tested using the same platform. These 2D and 3D board views show the above system as a whole once it's transitioned onto a PCB. The left shows the untraced design layout, or a rat's nest, and the right shows the 3D model of the design so far. So for next semester, once we return to work, I plan to focus my efforts on board design, mainly generating models, fabricating and testing the boards, and eventually integrating all the cable headers onto the single platform. And this will all be culminating to our finalized product to be presented at the 2023 Summit in the spring. And for now, I'll hand this off to my teammate Ricky, who will discuss the software side of our product.
Thank you, Griffin. Now, keep in mind, the block diagram is only possible if the firmware of the microcontroller allows for it. That, with our goal to be able to cover the largest scenario, the 170-pin cable, managing the code provided a decent challenge for us throughout development. In the end, our approach was to use a class to better structure our code. There's a lot going on in the class, but the main takeaway are the 2 public methods, the increment loop and the auto loop. These 2 allow us to individually check every pin or run through them all at once, and their outputs are on the right. This increment mode allows us to target any pin and verify its connection. Using the increment mode, pin 5 is being checked, and it seems like pin 5 is functioning well. And at the time this was taken, the cable size was set to 10, so pins 0 through 9 are being checked. Pin number 1, 2, 6, 7, 8, and 9 were disconnected, and the automatic mode allows us to see them all at once. Here are the mode methods in detail. A lot more is going on the screen, but essentially these two main blocks of code are our two methods. The left one, the incrementer method, works by using 3 variables for 3 layers of mux pairs that we have. Once one reaches the last pair, it goes back to 0 and increments the next, setting the port registers along the way. After these checks are done, the corresponding pin is read, and finally outputs to the LCD. For the automatic method, a nested for loop was used, one for each of the 3 layers. With the custom queue class, every iteration tests a pin, and if faulty, it will enqueue the pin number, and later dequeues all elements and displays them onto the LCD. This is the resulting flowchart of the code. How the modes are dictated is by a switch, and they both have access to 2 buttons for the end user. So far, the increment mode utilizes both, one for incrementing and one for decrementing the pins. The automatic mode just uses one, which is to start another round of checks. My future remaining technical accomplishments is to keep this functionality in mind for all sizes while limiting the overhead of the mode method algorithms, as they always accommodate the 170-pin cable. Essentially porting what I have to other sizes, or modifying the algorithm such that it breaks or loops back after a certain value. At this stage of this project, there were 3 main risks that were presented to us. The first would be any additional specifications that would come up throughout the design process. For that, we designed the system in a modular manner to accommodate for this. The second, of course, is the IC shortage. We had concerns that the shortage will affect lead times of attaining certain ICs, but luckily we were able to find substitutions and progress has largely been unaffected. Finally, third, was the Arduino reading a floating pin that would randomly detect as high or low. For this, we have implemented a pull-down resistor to pull any noise down and thus guaranteeing a signal for the Arduino to read. For our remaining technical accomplishments, there are 3 main goals that our team will focus on in the upcoming spring semester. The rest of the PCB headers will be needed to be designed, and so far there's only one left, the 170-pin header. We will also need to create a fabricated board where we will test the system with the various cables Vicor has provided us. And finally, a housing enclosure will be made to encompass the final PCB to give the board a place to rest in. As of this moment, we're confident in achieving the anticipated best outcome for the SCC. We were consistently on track with our development, and we will continue to do so. Finally, the team would like to thank our technical directors, Alfred Binder, Nathan Shake, and Daniel Hartnett for their continued support. And we'd like to give special thanks to our ELECOMP Capstone Program Director, Dr. Harish Sunak. Thank you.